All right, this video is going to cover an example that uses the Routh-Hurwitz criterion to determine stability for a closed-loop system. So let's take our example here or look at it. We're going to determine the stability of this closed-loop transfer function using the Routh-Hurwitz criterion. So if, let's say we have this block diagram here that represents a system, a closed-loop system actually, right? That has to do with this loop being here, right? So R of S is our input to our system. It's more like a reference input, let's say. E is an error term. We'll get into that later in the class. And then Y is our output to our system here. And then we have some sort of transfer function in that block in the middle. Our closed loop transfer function is if we were to rewrite this where it's just one giant block from R to Y, right? And we need to figure out what that would be. So how do we do that? Well, let's look at what our equation is for E based off of the first block diagram. E is just going to be R minus Y. And then Y is going to be equal to that big transfer function in the middle there times E, right? But we just defined what E was in terms of R and Y. We can solve this equation for Y and end up with our closed loop transfer function from our reference input R to our output Y, which is going to be 1,000 divided by S cubed plus 10S squared plus 31S plus 1,030. And that's our closed loop transfer function. We want to determine stability for this. So how do we determine stability? We need to use the Routh-Hurwitz criterion. So we're going to determine how many rows we should have. S cubed is our highest order term in our denominator here. That's n is equal to 3. So we should have 4 rows as a result. How many columns should we have here? Well, we take the ceiling of n plus 1 divided by 2, which is going to be 2 in this case. So let's draw out our Routh-Hurwitz table with 4 rows and 2 columns in this case, and we need to fill this out. So how do we fill out that first row? Next to S is S to the third. Well, we looked for the highest order term here, which is S to the third. We look at the coefficient in front of it. That's 1. Then we skip over the second one, go to the next one after that. That would be 31 here. And that's our entries for this first row. Then we go to our second row here. We don't start at S to the third, but we start at the next highest order, S to the second. That has a 10 in front of it. We skip the 31. We go to 1,030. Those are our entries for these other 2 pieces here, right? And what we need to do is figure out what our other coefficients in this table are, B1, B2, C1, and C2, right? And just as a note, for the Routh-Hurwitz, if you want to make the math easier for yourself, you could multiply a row by a positive constant, and the results would still come out the same. We're not going to do that this time, but we could have multiplied that second row by 0.1 if we wanted to, for example. Okay, so let's calculate those 4 coefficients here. So let's focus on B1. So for B1, we need the negative of some matrix divided by the coefficient that's directly the first coefficient that's in the row above what we're looking for. So that matrix there, how do we determine its values? Well, we go up a row, we go all the way to the left from where B1 is, right? And that's, we look at the entries there, that's our left column, so that's 1 and 10, right? Then we go to B1, we go up a row, we go 1 column to the right, which has 31 and 1030 in it. That's our right column for this matrix. We're going to take the determinant of that, make it a negative, and then we're going to divide it by going to B1, going up a row, going all the way to the left, that value there, which is going to be 10, right? And we can go through and crunch out what this number would be. And in this case, we'd end up with B1 being negative 72. Now for B2, what do? We go up a row. We go all the way to the left. We take those 2 entries there, which would be 1 and 10 again, right? And that's the first part of our matrix. We go up a row from B2, go 1 column to the right, and take the entries from the 2 rows above that, right? We don't have any entries in there, though, so it's just zeros. We divide it by the first coefficient in the row above. That's 10 again. B2 ends up being 0 in this case. Now that we've calculated B1 and B2, we can calculate C1 and C2 using the same procedure. So for C1, now it's 10 and negative 72, which is B1. and then 1030 and B2, which is 0, dividing it by the value that's above it, right, all the way to the left, -72 or B1 again. We can figure out what C1 is going to be. And for the same, using the same procedure, we get C2. Again, this would end up being 0 in this particular case here. So now we filled out our Routh-Hurwitz table, right? We have all our numbers. Now we can use the Routh-Hurwitz criterion to determine stability. So let's look at that first column and let's check how many sign switches there are here. There are 2, right? We go from 1 to 10, that's not a sign switch. They're still both positive. 10 to -72, that is a sign switch, right? So we flip signs once. -72 to 1030, that is flipping signs again, going from negative to positive. We end up with 2 sign changes in that column here. So what does that mean? We have 2 poles in the right half plane, which means that this system has to be unstable. Okay? And so that covers an example for how to use the Routh-Hurwitz criterion to determine stability for a closed loop transfer function.